Unit 5, Positioning. The data visualization process involves three key components. First is filtering and processing, where raw data is cleaned, organized, and refined to highlight what's important. Next is translation and visual representation, where the processed data is converted into visual forms like charts, graphs, or maps using appropriate visual encoding such as position, color, or size. Finally, we have perception and interpretation, where the viewer sees the visualization and makes sense of it based on their knowledge and the clarity of the design. Together, these steps ensure that data is not just shown but effectively communicated. This diagram explains the concept of layout positioning in data visualization, which focuses on how elements are placed in a visual design to convey meaning effectively. It highlights two main components, position and axis. Position is used to encode many discrete values, helping differentiate between multiple data points. Axis helps guide users through the data by limiting the search space, for example, using a top-down or bottom-up layout. The core of the diagram is placement and proximity, which determines the relevance of each data point based on how and where it is placed. This includes semantic distance, how conceptually related objects or ideas are influencing how intuitively users understand the layout. Relative proximity, the closer elements are to each other, the more closely related they appear. Absolute placement, items placed at the top are typically perceived as more important. Physical space, the direction and orientation of elements can influence user interpretation and navigation. Topic is impact of semantic distance and relative proximity on UI interface. In UI interface design, the semantic distance and relative proximity play crucial roles in enhancing usability. Semantic distance refers to the gap between what a user wants to do and how that intention is represented in the interface. A low semantic distance means that the interface uses familiar symbols, labels, and actions that align with the user's mental model. For example, a scissors icon clearly representing cut. When semantic distance is low, users can quickly understand and use the system. On the other hand, relative proximity deals with the physical closeness of related elements. Items placed near to each other are perceived as being connected or functionally related. For instance, placing a save button near an editable text area makes it easier for users to associate the two. If related controls are scattered or distant, users may struggle to understand their relationship. Together, reducing semantic distance and maintaining logical proximity between related elements make interfaces more intuitive, reduce errors, and improve overall user satisfaction. Relative proximity in UI design. Relative proximity in UI design refers to how closely related elements are placed together on the screen. According to Gestalt principles, when items are near each other, users naturally perceive them as part of the same group. This helps guide users through tasks and make the interface feel organized and intuitive. For example, in a login form, placing the username and password fields together with the login button just below clearly shows their relationship and supports a smooth workflow. On the other hand, if related elements are spaced far apart, users may become confused or misinterpret their purpose. To use proximity effectively, designers should group related items, use white space to separate unrelated sections, and keep consistent alignment to make the layout easy to scan and understand. Impact of axis styles on graph readability. Axis styles are key to how easily viewers can understand and interpret graphs. First, the scale selection, whether linear or logarithmic, directly influences perception. Linear scales are best for consistent, evenly spaced data like monthly sales. Logarithmic scales, on the other hand, compress wide-ranging values, making them ideal for data like population growth across centuries. Second, tick mark frequency and labeling matter a lot. Too many tick marks make a graph cluttered while too few reduce clarity. For example, financial charts often use monthly ticks with quarterly highlights to balance detail and readability. Clear, well-formatted labels like degree Celsius for temperature or familiar date formats help users quickly grasp the meaning of the data. In short, well-designed axes make graphs clearer, more intuitive, and more effective. Beyond scales and tick marks, other axis styles choices also shape how clearly data is understood. First, grid lines help with precision. Light, subtle lines guide the eye without overpowering the chart, while darker lines can highlight key reference points like quarterly benchmarks in economic charts. Second, axis orientation and placement matter. Most users expect time to move left to right on the x-axis, which matches reading habits. Dual axis, like for temperature and rainfall, must be styled carefully with different colors or positions to avoid confusion. Third, range selection is critical. Starting the y-axis at 0 can show an honest full picture, but zooming in on small ranges can highlight important details. Whatever the choice, consistency is the key. Using the same axis range across related charts ensure fair and meaningful comparisons. These axis design elements all contribute to making data easier to interpret and trust. Now this diagram shows how different axis styles can affect how easily we understand the graphs. In section 1, we see the difference between linear and logarithmic scales. Linear scales use equal spacing, so the growth appears more dramatic, while logarithmic scales compress large values, making exponential patterns easier to spot. In section 2, the focus is on tick mark frequency. The graph with too few tick marks make it hard to follow the data trend, while the one with optimal ticks strikes a balance. It's informative without being cluttered. Section 3 highlights the role of grid lines. Without grid lines, it's harder to estimate exact values. But with light grid lines, we get helpful reference points without distracting from the data. Altogether, these examples show that thoughtful axis designs through scales, ticks and grid lines greatly enhances readability and user understanding of visual data. The next topic is direct labeling and using keys or legends in graphical representation. Direct labeling means placing labels right on or next to visual elements in a chart like bars, lines or pie slices. This approach reduces the need for users to look back and forth between the graphs and a separate legend, making the chart faster and easier to understand. It works especially well for small or simple datasets where space allows for clean labeling. For example, if a pie chart shows sales for 5 products, adding labels like product A 25% directly on the slices give users instant clarity without any confusion on about which color or pattern matches which product. Legends or keys are sections placed beside or below a chart that explain the meaning of colors, symbols, or line styles used in visualization. They are especially useful when a graph contains many data points, overlapping elements, or categories that would be difficult to label directly without creating clutter. Legends help keep the chart clean and organized, making them essential in complex visuals like line graphs, scatter plots, or maps. For instance, in a line graph, comparing the annual performance of 10 companies using a legend to indicate which color or line style represents each company makes the chart far easier to read and interpret. So when making charts, we can label things in two ways, by putting the labels directly on the chart called direct labeling or by using a legend or key off to the side. Direct labeling is easy to read for small simple charts because the labels are right where you need them. But if there are too many labels, it can make the chart messy. On the other hand, using a key helps save space and works better for bigger, more complex charts. However, it takes more effort to read because your eyes have to move back and forth between the chart and the key. So direct labeling is best for clear and simple data, while keys are better for large charts with lots of information. Next topic is importance of logical and physical relationships in representing physical space in data visualization. Logical relationships show how different parts of data are connected, not where they are located in real life. This is important because it helps people see patterns or understand how things are linked. For example, a subway map might not show exact distance or directions, but it clearly shows which stations are connected and which line to take. Even if the map doesn't match real geography, it helps us to make decisions and find our way more easily. This kind of map focuses on the connections, not the exact physical space. Physical relationships. Physical relationships in data visualization show the actual layout of the things in real world. This means the distance, direction and the position of objects are represented as they truly are in physical space. These kinds of visualizations are very important when accuracy matters, like when someone is using a map to find their way, planning how to respond to a natural disaster, or designing a city layout. For example, a city map that shows real street locations and distances help people understand how far places are from each other and how to get around. Maps like satellite images, floor plans, and choropleth maps, which use colors to show data across areas, all use physical relationships to give a true to life picture of space. This helps people make informed decisions based on real geography. In data visualization, it's important to know when to show real world accuracy of physical relationships and when to focus on connections and patterns. Good visualizations often balance both depending on what the viewer needs. If the goal is to show how things are connected, like subway lines or internet networks, then logical relationships should be clear, even if the map doesn't match real distances. But if the task involves real world moments like planning a trip or responding to an emergency, then physical accuracy matters more. If these relationships are not shown correctly, it can confuse people or lead to wrong decisions. That's why choosing the right type of relationship for your visualization is very important. Next topic, color encoding in data visualization. Colors play a big role in making data easier to understand. We use colors in different ways depending on the type of data we are showing. For categorical data like names of companies or types of fruits, we use different colors like red, blue or green to show separate groups. This helps us easily tell one category from the other. For example, in a pie chart showing market share, each company is shown a different color so we can quickly compare them. For ordinal or sequential data like temperature or scores that follow a specific order, we use shades of the same color. Lighter shades usually mean smaller or lower value, and darker shades mean bigger or higher value. This helps us see patterns or changes in intensity. An example is a heat map where color shows how strong or weak something is. For diverging area, when we want to show changes from a middle point like profit versus loss, we use two opposite colors such as red and blue with a neutral color like white in between. This shows clearly which values are above or below the middle, like gain versus losses or negative versus positive opinions. Using color the right way makes charts easier to read and helps viewers understand the message quickly. But we have to be careful not to overload with too many colors or use confusing shades. Using wrong colors in charts and graphs can confuse people or give them wrong idea about the data. Here's how it happens. Inappropriate color scales. If we use colors like a rainbow or random bright shades for data that should show a smooth range like temperature or scores, it can be misleading. For example, using green and red to show small temperature changes might make the differences look more extreme than they really are. Lack of contrast. When the colors used are too small to each other or to the background, it becomes hard to see or read the chart. This is especially challenging for people with color blindness or poor vision. Too many colors. Using too many different colors at once can make a chart look messy and overwhelming. For instance, if every bar in a bar chart has a different color, it's harder to focus or compare the values clearly. Cultural and emotional biases. Colors can mean different things to different people. For example, red might be seen as a danger or loss, while blue might feel calm or positive. Using these colors in the wrong context can send the message wrong or confuse the viewers. That's why it's important to choose colors carefully, not just to make charts look nice, but to help people understand the data correctly and easily. Next topic is types of patterns used to group objects in data visualization. In data visualization, our brains are really good at spotting patterns. One common pattern is called proximity, which means that we naturally see things that are close together as a group. For example, in a bar chart, if two bars are placed very close to each other, like one for boys and one for girls in the same year, we automatically see them as a part of the same group. This helps us quickly compare the two values side by side. Why is this helpful? Because it lets us understand how things are grouped without having to think too hard or read every label. Just the way things are spaced on the chart can guide our understanding. Design tip. When creating a chart, placing related items near to each other helps the viewers immediately recognize which pieces of data belong together. Similarity. Our brains naturally group things that look alike. In data visualization, this means that if objects share the same color, shape, size, or direction, we see them as part of the same group. For example, in a scatter plot, if all the data points for one country are blue and another country's points are red, we immediately understand which points belong to which group without needing to read every label. This helps us quickly spot categories or repeated patterns just by looking. Continuity. When data points are arranged in a smooth line or curve, we see them as being connected or following a path. This is called continuity. For example, in a line graph that shows sales over several months, our eyes follow the lines to see how the numbers rise or fall over time. This helps us understand trends, progressions, or how something changes step by step. Together, proximity, similarity, and continuity makes it easier for people to read visual data quickly and accurately without needing to stop and analyze every part. These patterns are part of how our brains naturally organize what we see. Closure. Our brains are great at filling in missing pieces to see a complete picture. This is called closure. In data visualization, we use shapes, outlines, or shaded areas to suggest groupings, even if the shape isn't fully closed. For example, in a Venn diagram, overlapping circles show shared and separate areas. Even though they aren't always full borders around every section, we still see the full shapes. This helps us understand relationships and compare different groups easily. Enclosure. When we place objects inside a box or shaded area, we naturally see them as belonging together. In dashboards, for instance, we might put all the sales metrics in one section and the marketing metrics in another, each inside its own box. This makes it easier for viewers to focus on specific areas and quickly know what data belongs to what topic. Connections or links. When two items are connected by a line or arrow, we immediately see them as related. This is used in flowcharts, network diagrams, and organizational charts. For example, in a company org chart, lines between boxes show who reports to whom. This pattern helps us understand structure, direction, and relationships between different elements. Together, these patterns, closure, enclosure, and connection, use our natural visual instincts to guide how we understand and organize information in charts, diagrams, and dashboards.